Welcome to question 17 from the 2020 TMUA paper 1. The question asks us to find the complete set of values of m in terms of c such that the graphs of y equals mx plus c and y equals the square root of x have 2 points of intersection. We are given 6 possibilities. Pause the video, read through these possibilities and have a go at answering the question for yourself. Okay, let's begin the question by drawing a sketch of the graph of y equals the square root of x, which looks something like this. And then if we had a line y equals mx plus c, that's a straight line with y-intercept at c and gradient m. So if we had a graph like this, then we could see that would intercept the curve square root of x in exactly 2 places, which is what we want. But where would this go wrong? Well, if we have the same value of c, the same intercept, we can see if we have a graph with gradient that is negative or equal to 0, then we'll only intercept the graph once. And if we have a graph with a line with gradient equal to some critical value, which we'll call k, then we will have a tangent line which will just touch the graph once. And in fact, if we have an even steeper graph, then it won't intercept the line at all. So with this in mind, let's think about a few different cases. Firstly, let's think, well, if c is negative, so the y-intercept of the line is negative, then how many intercepts can we have? Well, we might have no intercepts if the line comes down like this, and if the line is positive, then we'll have exactly 1 intercept. So in that case, we can see we'll have 0, 1 intercepts, but we certainly can't have 2. Now, next, let's think about when c is greater than or equal to 0, but the gradient is less than or equal to 0. So we're going to be some case that looks sort of like this red line or is even lower than it. Then we can see that we'll have exactly 1 intercept. So again, we won't have 2 intercepts. Now, what about if c is greater than or equal to 0, but m is greater than or equal to k, so the gradient is at least as steep as this red line here? Well, then we can see that if m equals k, we'll just touch the curve y equals square root of x, and if m is greater than k, we won't even touch it at all. So in that case, we will have 0 or 1 intercepts. So now the only case we haven't considered is where c is greater than or equal to 0, but the gradient is strictly between 0 and k, where k is this critical value of the tangent line. And when that happens, we get something like the green line, which we can see intercepts the curve in 2 places. So therefore, the case that we need to look for is the case where m is strictly between 0 and k. So in fact, what we need to do in order to find the range of values of m is to find this critical value k. So this is the complete range here. So let's move on to a new page and try to find this critical value k. Okay, so here's a smaller sketch of our setup, and we've deduced that there are 2 intercepts if and only if c, our y-intercept, is greater than or equal to 0, and m is strictly between 0 and k. But what is k? Well, k is this special value of the gradient m, such that even when we have c greater than or equal to 0, if m equals k, then we have just 1 intercept between the curve y equals square root of x and the line y equals mx plus c. So we can describe it as being the positive value of m, because we need the gradient of this line to be positive, such that there is only 1 intercept between the 2 curves when c is greater than or equal to 0. But how can we write this mathematically? Well, what is an intercept between the line y equals mx plus c and the curve y equals the square root of x? Well, it's a point where mx plus c equals the square root of x, and in this case we want m to equal k, so it's equivalent to saying that there is only 1 solution to the equation kx plus c equals the square root of x, and k is positive and c is greater than or equal to 0. So this is how we can characterise what k is, and now we need to use this statement in order to find k in terms of c, and then we will have our complete set of values of m in terms of c. So how can we solve this equation? Well, if we move the square root of x onto the other side, then we see we have kx minus square root of x plus c equals 0. And we're still working in the case where k is positive, c is greater than or equal to 0, and it only has one solution. So why is it useful to have moved square root of x onto this side? Well, we can now see that this is just a quadratic expression in the square root of x. And since it only has one solution, what do we know about a quadratic equation that only has one solution? Well, it means that the discriminant must be equal to 0, because if this only has one solution for x, it must only have one solution for the square root of x. So if the discriminant equals 0, what does that mean? Well, the discriminant here is minus 1 squared, which is 1, minus 4 times k times c. So that needs to equal 0. So if this equals 0, then this equation will only have one solution. And that tells us that, therefore, if we move the 4kc onto the other side and divide through by 4c, that k must equal 1 over 4c. And therefore, we can rewrite our criteria here as having two intercepts if and only if c is greater than or equal to 0 and m is strictly between 0 and 1 over 4c. And in fact, this second inequality here implies that c is greater than or equal to 0, so we can just write this as m is strictly between 0 and 1 over 4c. So therefore we see that this is the complete set of values for m, in which we have two intercepts between the line y equals mx plus c and the curve square root of x. And if you refer back to the options given at the start of the question, we can see that this is just option A. So our answer to the question is A.